Hello everyone, this is Miss Crute, and today we are going to be working on analyzing graphs of polynomial functions. So a polynomial is a mathematical expression consisting of terms being added, subtracted, multiplied, or divided, where all of the exponents on variables are whole numbers. So for example, we could have 3x to the 5th minus 6x. That's a polynomial because there are only exponents that are not zero and not fractions. Then we could also have negative 7x to the 50th plus 30x to the 72nd. Oops, sorry, I meant to write 27. Wrote that a little backwards. Minus 50. And that would be a polynomial because the exponents are all positive and they are not fractions. So let's look at two types of polynomial functions. We could have even or odd. A polynomial function is even if the highest exponent is even. So if we look at our two examples, this one would be even because the highest exponent is 50. A polynomial function is odd if the highest exponent is odd. So looking at our examples, this one has an odd exponent for the highest one, so that's an odd function. So this is important because we use this information to determine the end behavior of polynomial functions. The end behavior of a polynomial function is the behavior of the graph as x approaches positive infinity or negative infinity. So we're going to use this table below to help us organize the end behavior of different types of polynomials. Something that we're going to also be talking about here is the sign of the leading coefficient. That's what LC stands for. So, for example, if we looked up here, the first function, 3, would be the leading coefficient because it goes with the term that has the highest exponent. If we look at the second example, negative 7 would be the leading coefficient because the highest exponent is 50 and negative 7 is with that term. So degree and the sign of the leading coefficient affect what our end behavior is going to look like. So if we have a polynomial that has an even degree, and it had the sign of the leading coefficient is, that means that as x goes to negative infinity, that f of x is going to go to positive infinity. So I'm going to just draw a little sketch so that you know what I'm talking about when I say as x goes to negative infinity. That means that we're concerned with what the left end of the graph is doing. So if I've got a graph that looks like this, and we're talking about x going to negative infinity, we want to know which way this arrow is pointing. Since in this case, I know that an even degree and a positive leading coefficient means it's going to go up, so that's positive infinity. All right, and then if we're talking about x going to positive infinity, that means we're concerned with the right side of the graph. So I'm going to draw another random graph here. And so if we're talking about x going to positive infinity, we're talking about the right arrow. So if we have an even polynomial with a positive leading coefficient, as x goes to infinity, f of x will also go to infinity. So a sketch of this specific example could be something like this. Both ends are going to be pointing up. Now, if I have an even polynomial that has a negative leading coefficient, that's going to flip my function upside down. So that means as x goes to negative infinity, f of x is going to be going to negative infinity also. And then as x goes to positive infinity, f of x will still be going to negative infinity. So an example of this type of graph, we could just draw an upside down parabola. Right, then if we have a polynomial with an odd degree, and it has a positive leading coefficient, that means that as x goes to negative infinity, f of x is also going to go to negative infinity. As x goes to positive infinity, f of x is going to go to positive infinity. So for an example of that graph, I could draw something that looks like this. And then the last situation we could have is if we have an odd polynomial with a negative leading coefficient, that's going to flip one we just did upside down. So that means as x goes to negative infinity, f of x is going to go to positive infinity. And as x goes to positive infinity, f of x is going to go to negative infinity. So for example, we could have something that looks like this. And I'm going to go back, and next to each example, I'm going to write in an example of what that polynomial could look like. So if I'm talking about an even and positive, that could be something like x to the fourth plus 3x minus 7. The highest degree is positive, the highest degree is even, and there's a positive number in front of the leading coefficient. If I had an even with a negative leading coefficient, that could be something like negative 2x to the sixth plus 3x squared minus 8. We've got an even number for the highest exponent, and we have a negative leading coefficient. If we're talking about an odd one, then that could be something like 8x to the third minus 6x plus 9. We have an odd exponent and a positive leading coefficient. And then an example for this last one could be negative 15x to the seventh minus 3x. We've got an odd number for the highest exponent and a negative for the leading coefficient. So those are just examples of what they could look like. They don't necessarily match our sketch. So the degree is also really, really important because it tells us the maximum number of zeros a function has. For example, f of x equals 3x to the fourth minus 5x plus 2 has at most 4 zeros because the highest exponent is 4. This next one, f of x equals negative 4x to the fourth plus 4x to the third minus 2x squared plus 3x minus 12. That also has at most 4 zeros because the highest exponent is 4. So even though those functions look really different, they have the same maximum number of zeros because they have the same degree. Alright, so now just a couple review vocab words. A local maximum is a point which is higher than all the other points in the immediate vicinity of the point. So this would be an example of a local maximum. A local minimum is a point lower than all of the other points in the immediate vicinity. So that's an example of a local minimum. Another important thing we need to know is an interval. An interval is a specific part of a graph function given two endpoints in terms of x. This is super important that x's always go from left to right. So here we've got three different intervals. Negative infinity to 0 would be this first interval over here because negative infinity is indicated by that arrow and it stops right here, which would be 0. Remember, we're talking about the x values. This next interval would be from 0 to 5 because we start at 0, it ends right here at an x value of 5. And then this would be the last interval because we're starting at 5, and then since there's an arrow over here, it's continuing on forever. The reason we talk about intervals is because we talk about where functions are increasing or decreasing. So we want to state whether it is increasing or decreasing at each interval. So if we look here, I'm going to divide it into all of my intervals. So now if we look here, remember we're always moving from left to right. So if I'm going from left to right on this graph, I'm going up. Since I'm going up, that means it's increasing. And the next one, if I move from left to right, I'm going this way, which is down. So that means that is decreasing. And then in the last interval, if I start at the left and go right, I'm going up. So that means this one is increasing also. Alright, so now we want to put everything we just talked about together. I know this seems like a lot and super overwhelming, but it gets really easy once you practice. So the first thing we want to write are the local maximums. We want to give those as ordered pairs. So I can see I've got one here, one here, and one here. So I've got -8, 4. I've got 0, 6. And 9, 10. So we actually had 3 local maximums. Now I want to find my local minimums. So I've got one here and one here. So I've got -4, -3. And then I've got 3, -2. Now we're looking for increasing intervals. So I'm going to go ahead and divide my graph everywhere that there's a local min or a local max. I'm going to put a dotted line. So here's a local max. So I put a dotted line, dotted line, dotted line. Got a lot of intervals happening here. Then I'm going to start at each interval. I'm going to put in the arrow to show which direction it's going because that's going to make it really easy to write if it's increasing or decreasing. So, again, we're just looking at if we move from left to right in that interval, which way it's going. So now I'm going to write the increasing intervals only. So we've got from -infinity. Oops. So we've got when at -infinity is less than x is less than -8. That's increasing because the arrow's going up. We've also got -4 less than x less than 0. That was this interval right here. And then we've got one more over here. We've got from 3 to 9. Those are the increasing intervals where the arrow is going up. I want you to go ahead and write in the decreasing intervals. Alright, then we want to look at the end behavior. As x is going to infinity, since it's infinity, that's positive, we're looking at the positive end. F is going to -infinity. It's going to -infinity because it's going down. Then as x goes to -infinity, negative, we're looking at the negative side. So over here, f is going to -infinity also because that arrow is pointing down. The x-intercepts. Man, I need some new colors. Let's go with this. So x-intercepts, I'm looking for everywhere the graph crosses the x-axis. I've got 1, 2, 3, 4, 5, 6 x-intercepts. So I've got -10, 0, -7, 0, -1, 0, and then I want you to go ahead and write the last 3 in. Alright, y-intercept. If it's a function, there's always only one y-intercept, and we've got that right here. That would be at 0, 6. Alright, then we want the number of real solutions. For that, we just count up the x-intercepts. 1, 2, 3, 4, 5, 6 x-intercepts. And since there are 6 x-intercepts, we know there are no imaginary solutions. That's something we're going to talk more about tomorrow in class. Alright, and we have one more type of problem to go over, but unfortunately, we are out of time. So we are going to go over that as well tomorrow in class. Alright, good luck.